all of you are doing good, and today I am here with a video on class 9th science, force and laws of motion. Now this is a very important topic in terms of the concept, and as you go to your higher classes you are going to learn more about this topic. So it is very important that you get your basics right and you get a crystal clear conceptual understanding. So some of the topics that we will cover in this video are balanced and unbalanced forces. In fact, even before that, what's a force? Then we will cover Newton's first law, second law and third law of motion, and finally we will look at conservation of angular momentum. So we will cover this entire lesson in two videos. The first video will focus on the theory and the concepts with examples. The second video will focus on problem solving, as in numericals and questions, which is one of the toughest part in physics. So be with us and watch this entire playlist on force and laws of motion. Let's get started. Let us see the cause of motion. Now, what is the cause of motion? An external force. What is an external force? Okay, let us see. Let us look at this example. Do you think that, suppose if you have a ball, do you think that a ball ever moves on its own? If it does, we fear that it is some magical or mysterious event that is taking place, right? So normally a ball, when kept on a table, will never move on its own. It will be at rest. It will move only when you apply some force on it, right? So external force is needed to make a stationary body move. So that means a body which is at rest will be in motion only when an external force is applied. Similarly, let us suppose a body is moving, right? So do you think that the body stops on its own? Yes, it does sometimes. Let us suppose you applied some force on the ball started moving. But will it keep on moving indefinitely? Not at all, right? After some point of time, it will stop. So why do you think that the body stopped? The body stopped because again there was an external force which was applied on it. And what was that force? That is frictional force, right? So let us not concentrate much on frictional force and all those stuff here. Here, what I'm trying to say is a body which is at rest will start moving when an external force is applied on it. Similarly, a body which is moving will come to rest only when an external force is applied on it. So that means force is the cause of motion. Force can make a body move. Force can stop a moving body, right? Now, in different scenarios, you have different types of forces acting on a body to make it move or to stop it, right? So we will talk about all those scenarios in detail one by one. I mean, we will not get into the depth at the very beginning, right? So gradually, step by step, we will talk about everything. So now we got reply to our question, what causes motion? It is force that causes motion. So let us quickly talk a bit about force, that what is force. So here, right now I will focus my study only on motion, right? So now for that, we will talk about these two categories of force, that is balanced and unbalanced forces. What is a balanced force? What is an unbalanced force? We will talk about this because this is going to help us to understand the motion of objects. So what are balanced forces? Balanced forces are equal and opposite forces. As the name says, balanced. You would have heard of things like spring balance, beam balance, weight balance. Balance means to make things equal on both sides, right? You would have gone to a grocery shop and you would have seen the balance which they use to measure things, right? To measure the weight of objects, right? So balance means it has to be equal on both sides. So forces which are equal and opposite. Equal and opposite means the forces are equal in magnitude but opposite in direction. I have already spoken about magnitude and direction in the previous lesson while I was talking about scalar quantity and vector quantity. What is magnitude? The numerical value which defines the measure of a quantity. For example, when I am talking of force, What is the unit of force? It is Newton, right? So let us suppose if there is a force of, let us suppose this is one object. So if you apply a force of 1 Newton in this direction, then another force of 1 Newton is applied along this direction. So that means magnitude of both the forces are same. What is the magnitude? It is 1. So 1 Newton is the magnitude. So magnitude of both the forces are same. So we say that they are equal forces. And they are in opposite direction. That is why we say they are equal and opposite. So equal means they are equal in magnitude. Opposite means they are opposite in direction. Right? So force again is a vector quantity. I am sure you would have studied about the basic of forces, that what is a force, what is the SI unit of force, how do we calculate force in your previous classes. Even if you have not studied, you will study about it in this lesson itself as we go ahead. So balanced forces do not cause any change in motion because they are equal and opposite. So if you are trying to pull something, now what do I mean when I say that you apply a force of 1 Newton in this direction? That means you are trying to bring this object, make this object move along this side. Now when you apply another force of 1 Newton along this side, that means you are trying to move this body along this direction. Now on both the directions you are applying the same amount of force. So what will happen to the object? The object will not move in any of the directions. So these balanced forces do not cause any change in motion. So the best example that you can think of when trying to understand balanced force is the example of tug of war. I am sure most of you would have played this tug of war, right? What happens? There is a team. There are 2 teams on each side, and then you have a thick rope which both the teams try to push on both ends. Now what happens? When both of them, so this team 1 is applying a force along this direction, and this team 2 is applying another force along this direction. Now when both of them are applying force, now the forces are opposite in direction, that is for sure. Now when the magnitude of the forces are the same, when the forces are equal as well, then what happens? It is in this condition, when none of them wins, because both are applying equal forces on both directions, right? Now what happens if the forces are not equal? So there comes the unbalanced forces. So unbalanced forces are the unequal forces. That means the magnitude of the force in one direction is greater or smaller than that of the other direction. So in this case, the forces can be in the same direction or opposite direction. So let us suppose if you have an object, there can be 2 scenarios. Either the magnitude is different or the direction is different. Let us suppose this is your object O. You apply a force of 1 Newton along this side, and you apply a force of 0.5 Newton along this side. So what will happen? A greater force is being applied along this direction, so the body will start moving along this direction, right? Now there can be another scenario where you have this object O, you apply a force of 1 Newton along this direction, you apply another force of 1 Newton along the same direction. So in this case you can see that the forces are equal, but they are equal in magnitude, but they are also along the same direction. So what is happening? The net force along this direction is 0 and the net force along this direction is 2 Newtons. Therefore the body will start moving along this direction again, right? So we can see that unbalanced forces causes a change in motion, right? So in this case again you can think of the example of tug of war, when let us suppose if the force along this side is more, then the entire thing gets pulled along this direction. That is, the motion takes place along this direction, and this party at that instant of time is considered to be winning, correct? So this is the concept of balanced and unbalanced forces. So if balanced forces are acting on the body does not move. I mean, I'm not saying the body does not move, there is no change in the motion of the body. Now, when we talk of unbalanced forces, it causes a change in motion because the forces which are acting on the body are unequal forces acting along the same direction or opposite direction. So this is a quick review of balanced and unbalanced forces. So the fact which will help us in as we go ahead with this lesson is that balanced forces does not cause a change in motion, whereas unbalanced forces cause a change in motion. Let us now talk about the different laws of motion. These laws of motion were a very critical concept which laid the foundation of a major part of physics. So there were three laws of motion which were given by Sir Isaac Newton, which actually helped us to understand the concept behind motion, which helped us to understand three important facts about the phenomenon of motion taking place in a body. So now there were different other scientists as well who did a lot of study and research on force and motion, because force was the cause of motion. So they were trying to study the relationship between force and motion, right? So the first scientist to do research and study on this was Aristotle. After Aristotle, it was Galileo who gave some of the concepts related to force and motion, and then came Sir Isaac Newton, who actually gave the three important laws of motion, which are known as Newton's laws of motion, which actually became the pillar of Newtonian mechanics, right? And that is why it came to be known as Newtonian mechanics, right? So now let us start with Aristotle's law of uniform motion. Aristotle gave an idea. While scientists were trying to know the cause behind motion, even though they found that force was the cause behind motion, they were trying to give some theory of how the motion takes place, or how is it related to force. So Aristotle studied uniform motion. What is uniform motion? We have spoken about it in our previous chapter. Uniform motion is the one where the body moves with uniform velocity, right? So the body moves with constant velocity. So Aristotle told that an external force is required to keep a body in uniform motion. So Aristotle said that, let us suppose if there is an object which is moving with uniform velocity. So in order that the body keeps on moving with uniform velocity, it is needed that an external force is continuously being applied on the body. That means not only to start the motion, but also to retain that uniform motion, an external force has to be there. He told this on the basis of these kind of examples. Suppose if you have a box tied to a string, and this person is dragging it. Now, as soon as he leaves the string and he moves off, what happens to the box? The box comes at rest. It is not moving anymore. So that means Aristotle told that it moved so far because an external force was being applied on it. Now it stopped because the external force has been removed. So Aristotle's conclusion was that if you want an object to be in uniform motion, a force has to be applied on the body continuously. As soon as the force is removed, the body will stop. That was Aristotle's idea. But the fallacy or the failure in Aristotle's principle lied in the fact that whatever he observed was correct. The example which I told, the observation was correct, but what he interpreted from that observation was not correct. Aristotle thought an external force is required to keep a body in uniform motion. But actually, why did this happen? Why did the body stop? Or what was the external force actually doing? Now, at the moment a body starts moving on the ground, there is a frictional force which continuously acts on the body. And what is a frictional force? Frictional force is a resistive force. That means a force that opposes motion. It always tries to oppose motion. It doesn't want the body to move, right? So the frictional force is continuously acting on the body, and that because of the frictional force, the body cannot move. The body can move only when an external force is applied to overcome the frictional force. So in this case also the same thing is happening. In the beginning, an external force is being applied. This external force is winning over the frictional force, and that is why the body is able to move. But after some time, as soon as the external force is removed, what happened? The frictional force dominates and the body stops. So it is not that the force or the external force alone is the one who is responsible for a body to be in uniform motion. The frictional force also has a role to play. Now let us imagine a situation where you do not have any frictional force. However, in reality or in your real life, you will have frictional force on every surface. But let us assume, let us imagine for a minute that there is no frictional force at all. That means there is no friction there. The surface is extremely smooth and slippery, and there is no frictional force being applied on the object. In that case, what would happen? Do you think that an external force would be needed to move the body? No, because there is no force now to stop the body. So the body will move on its own. Right? So if the surface is frictionless, the body will move on its own. There is nobody to stop the body. So when there is nobody to stop the body, you don't need anybody to oppose the frictional force, because the frictional force itself is not there. So that means the conclusion was that an external force is definitely required to keep a body in motion, but that is true only if the resistive forces are present. That means only when resistive forces like frictional force or viscous force is normally found in liquids, right? So when your resistive forces are present, only then you need an external force to keep a body in motion, because that external force will actually defeat the frictional force and make the body move. But when you do not have any resistive force, there is no force to stop the motion of the body. So the body will move on its own. So in that case, you do not need an external force to keep a body in motion. So you understood what was Aristotle's idea and what was the fault in his idea. I mean, whatever he observed was correct, but what he interpreted out of that was not completely correct. Right? So this was Aristotle's fallacy. This is where the Aristotle's idea failed. Now, based on this fact, Galileo gave his law. So Galileo also did lot of studies on force and motion, and what did he say? He told that a body moving on a frictionless surface should move with constant velocity. That's what I mentioned, right? So if the surface is frictionless, in that case, there is nobody to stop the motion or to oppose the motion. So in that case, the body should keep on moving with uniform velocity. That is constant velocity. Because when we are not applying any external force, when we are not disturbing the body at all, that means the speed or the velocity of the body should not increase or decrease. The velocity will increase only when you give some external force or something. The velocity will decrease again when there is some frictional force or something. So if there is no disturbance at all, the body is moving on its own on a frictionless surface, in that case it should move with constant velocity. That is, it should be in uniform motion. Let us look at this example. We have a rough surface. On a rough surface, how does a ball move? It experiences the ups and downs. That is actually, it is experiencing the frictional force, which is at every moment trying to oppose its motion. Whereas in case of an extremely smooth surface, the body just moves with a constant velocity, right? So now, what was the conclusion of Galileo's idea? So Aristotle's law was falsified by Galileo. So let's have a quick review. What did Aristotle say? He told that an external force is continuously needed to make a body in uniform motion, to keep a body in uniform motion. But Galileo said that external force is needed only if the resistive forces are present. If the surface is a frictionless surface, in that case, we do not need any external force to be applied on the body to retain its uniform motion. So in other words, Galileo said that for a body which is at uniform motion, the net external force acting on it is equal to 0. So according to Galileo, a body at rest is considered equivalent to a body in uniform motion, because when you consider a body at rest means it is not at all moving. So the net external force on this body is equal to 0. That means, does that mean that there is no external force acting on the body? No, not at all. That is why I spoke about balanced and unbalanced forces. Maybe balanced forces are acting on the body. Maybe there is an object like this. There are so many forces acting on the body, but they are all balanced forces. That means, let us suppose if some force F is here, F is here. They are equal and opposite forces, so they cancel out. Similarly, some F1 is here, F1 is here. They are again equal and opposite, cancel out. So the body is at rest. So this means when a body is at rest, when the net force acting on the body is equal to 0, that means a body is under the influence of balanced forces. Right? And he told that there is another scenario where the body is in uniform motion. Now, even in case of uniform motion, what is happening? The body is moving with a constant velocity. So in case of constant velocity also, the net force acting on the body is equal to 0. Because when some external force is applied on the body, what happens to the velocity? The velocity also increases. Or when you apply some obstruction to the motion of the body, the velocity decreases. So in this case, when you are considering a frictionless surface, that means there is no frictional force, there is no external force needed. In that case, the body is moving in with uniform velocity. So even in case of uniform motion, the net force acting on the body is equal to 0. So Galileo told that a body at rest can be considered equivalent to a body in uniform motion. Right? So that was Galileo's idea. So initially, as I said, there were many scientists who wanted to know about the motion, the cause of motion, relationship between force and motion basically. So many of them were doing studies and research on this. So initially their focus was completely on uniform motion, that what happens during uniform motion, because they were trying to understand the simple things first and then they were trying to look at non-uniform motion. Right? So Galileo told that Aristotle was incorrect. He corrected Aristotle's law. Then he told that a body at rest can be considered equivalent to a body in uniform motion. That's because in both the cases, the net force acting on the body is equal to 0. Right? That doesn't mean that there is no force acting on the body. Thereafter, based on these Galileo's ideas, Newton did little more research and he came up with the first law of motion. So what was Newton's first law of motion? It stated that a body at rest tends to remain at rest and a body in uniform motion tends to remain in the state of uniform motion until and unless an external force is applied on it. So the first law of motion spoke only about the scenario of uniform motion. So it said that, so even Galileo told something similar to this, right? So Galileo's law formed the basis of Newton's first law of motion. But what was special about, you might say then why Newton's first law is so famous, it should have been called as Galileo's first law of motion. That's because Newton studied not only this portion of uniform motion, he also extended his studies and he also spoke about the scenario of non-uniform motion. So that is why he gave little more information about force and motion, and that is why all the three laws came to be known as Newton's first law, second law and third law respectively. So Newton says that a body which is at rest, it always wants to be at rest only. Similarly, a body which is in uniform motion, it always wants to be in uniform motion until and unless some external force is applied on it. Let us suppose if you have a ball at rest, that is the ball is lying on the table. The ball will want to lie on the table for hours together, for days together, for years together if you don't apply an external force on it. So something which is at rest always will be at rest until and unless you apply some force on it. Similarly, something which is in uniform motion, that means it is moving with constant velocity. So this will also keep on moving with constant velocity. So when will it move with constant velocity? When it is on a hurdle-free surface, a frictionless surface, right? So it will keep on moving with the same constant velocity until and unless you apply some external force on it to stop it. So this was Newton's first law of motion. A body at rest wants to be at rest. Body in uniform motion wants to be in uniform motion until and unless an external force is applied on it. So let us look at the first law from the point of view of balanced and unbalanced forces. How can we state the Newton's first law using the concept of balanced and unbalanced forces? A body at rest tends to remain at rest and a body in uniform motion tends to remain in the state of uniform motion until and unless an unbalanced force acts on it. That means, that's what I told earlier also, right? That if a body is at rest or if the body is at uniform motion, that means the net force on the body is equal to 0. That doesn't mean that there are no forces acting on the body. That means either there are no forces acting on the body or the body is under the influence of balanced forces, right? Because balanced forces does not cause any change in motion. Now, if we want, according to the first law, if the body at rest will remain at rest, the body in motion will remain in motion until and unless we apply an unbalanced force on it. What will happen if an unbalanced force is applied on the body? The moment an unbalanced force acts on the body will be set in motion, right? Because unbalanced forces cause a change in the motion of the object, right? So, for example, in the first, and the ball doesn't move at all. The ball is at rest. Why is it at rest? Because it is under the influence of balanced forces. Now, this ball, if you see, the ball is moving, right? Now, the ball will keep on moving as long as the ball is moving with uniform velocity. It will keep on moving with uniform velocity as long as it is under the influence of balanced forces. As soon as you apply an unbalanced force on it, what will happen? The ball will stop, right? So the balanced forces do not cause any change in motion, whereas an unbalanced force causes a change in motion of the body. Okay, so with this, we completed Newton's first law of motion. Now, did you notice that here we spoke about the tendency of the body which is at rest to remain at rest, and the tendency of the body which is in uniform motion to remain at uniform motion, right? Now, this tendency of an object is known as inertia. So now we are introducing a new term. So I guess inertia is a new term to all of you. So inertia is nothing but a tendency of an object to remain in its present state. So inertia is the resistance of a body to change its state of motion. So when I say to change its state of motion, the state of motion means it can be at a uniform motion, it can be at rest, whatever its state may be, it will always try to resist its present state. For example, a body which is at rest, it will always want to be at rest. So when you try to make it move, the body will offer some resistance. So that is known as inertia. So let us take this example. Let us suppose if you have a ball at rest. So this ball would like to be at rest, right? So even if you try to apply some external force, initially the ball will resist that external force. But after that, when that force dominates, the ball starts moving. Similarly, a ball which is already moving, it will want that it keeps on moving. It will not want to come to rest, right? So this property is known as inertia. So we will take some very good examples from our day-to-day life, which all of us would have experienced sometime or the other. Have you ever experienced jerk when brakes are applied suddenly? Let us suppose you are sitting inside a car, suddenly the driver applies brakes. What happens? You feel a jerk. Why do you feel a jerk? He applies a brake, the car's velocity suddenly slows down. The car suddenly slows down. So earlier, what was happening to the car? Well, if you look at this car, suddenly when you apply brake, the person who is sitting inside, he feels a jerk. You tend to bend when the brake is applied. That is because initially the car was moving, right? So the car was moving with a uniform velocity. So for the car, its current state of motion is this velocity v. So it wants to move with this velocity. But when you suddenly apply brake, the car resists. The car doesn't want to change its initial position. Its current position. So the person sitting inside also, this man, he wants to be in his current position. So what happens? The man is trying to be in his current position, but the car is moving forward. As a result, he experiences a jerk, right? So every object tries to retain its current position. Similarly, if you look at this example, that there is a tendency to bend on one side on a bike during sharp turn. Let us suppose if you go to some hilly areas or something, you would have seen that the roads have very sharp edges, right? The turns are extremely sharp. So when you take those turns, the person sitting on the bike or cycle, they tend to bend. Have you observed this? Look at this bending when they are taking this turn, right? So this bending also takes place because of inertia, because the body wants to be at the same position, but because of the turn, the vehicle moves along the direction of the turn, and as a result, the body bends. Right? So there are many other examples. For example, when you would have seen a cup and a saucer. I mean, normally when some guests come to our house, we serve them tea or coffee in a cup and saucer. So have you seen the design of the saucer? It is little outwards and it has a depth inside. Why is it so? So that the cup doesn't fall off. Because if it is completely plain, if let us suppose if this is your cup and if this is your plate, and there is another scenario where this is your cup and this is your plate. So because of this sharp edges, it actually prevents the cup from falling down, because this cup will have its inertia, it will always want to be in the same position. Now let us suppose if this plate is moved a bit, the cup might fall down, right? Similarly, you would have seen this example that let us suppose if you have a tumbler. On this you have played a thin card and above that you have placed a small coin. This is a very popular example of inertia. Now if you flick this card, what happens? The card is thrown off, and what happens to the coin? The coin should also get thrown off along with the card, but actually the coin falls into the tumbler. That's because the coin still wants to hold its current position. The coin doesn't want to leave its current position. So even though the paper is thrown away, the coin falls into the tumbler. Right, so these are some of the examples of inertia. So inertia has a very important role to play when we talk of force and motion. Because not only force, in fact motion, because all these examples which I have demonstrated, they are all related to motion. During the movement of objects, we see that there are at times where inertia plays an important role, and because of which we experience such bending during sharp turns or jerks when a vehicle is slowed down suddenly. So now we will start with Newton's second law. So far we talked about Newton's first law, and I hope that is clear to you. So let us try to understand the second law. Newton's first law was for scenarios where net force is equal to 0. That means Newton's first law basically talked about uniform motion. It spoke nothing about non-uniform motion. It only told that object at rest will try to be at rest, object at uniform motion will try to be at uniform motion, until and unless you apply some external force on it. So now in Newton's second law, it is for scenarios with net force not equal to 0. That means here some external force is applied on the body, right? So you are clear with the fact that in the first law we were only talking about uniform motion, right? So now we will talk about a general scenario where there is an external force which is also acting on the body. Now before we start with Newton's second law of motion, we should know what is momentum. So momentum is again a new term for you. It is a new quantity which is going to get introduced. So let us see what is momentum. Momentum is the product of mass of a body and its velocity. Quite simple, right? Let us suppose if you have an object of mass m which is moving with velocity v, then we say that momentum of that object is equal to m into v, right? It is a vector quantity because it has both magnitude and direction. So that's quite obvious also, because if momentum is product of mass and velocity, velocity itself is a vector quantity, right? So momentum should also be a vector quantity. It is generally denoted by a small p. Normally we denote momentum by a small p, and it is equal to m into v. Let us look at this example of momentum. Let us suppose if you have a ball of mass 1 kg moving with a velocity of 10 meters per second, then what is the momentum of this body? It will be mass into velocity, that is 10 kg meter per second. So when I talk about the unit of momentum, it is simple. For mass, the unit is kg. For velocity, it is meter per second. So for momentum, it is kg meter per second. This is the SI unit of momentum. So in this case, a ball of 1 kg moving with velocity of 10 meter per second. What is the momentum of this ball? Momentum would be 10 kg meter per second. Right? Okay. So now let us try to look at the dependency of force on mass. How is force dependent on mass? Now, why are we studying the dependency of force on mass? Because we want to just now I introduced momentum, right? Why did I introduce momentum? Because momentum played a role in Newton's second law of motion. In second law of motion, Newton basically told that there exists a relationship between force and momentum. Right? So we want to see that relationship between force and momentum. So in order to see that, what are the two quantities on which momentum is dependent? Momentum is the product of mass and velocity. So we want to see the dependency of force on mass. Again, we will see the dependency of force on velocity. So that is how we will see how is force related to momentum. So let us look at the dependency of force on mass. Scenario 1. Force required to push object with same velocity. Let us suppose you have two different objects. What are the objects here? These two kids. So in the first case, if you see, mass of the object is greater. That is quite obvious, right? So the mass is heavier. So in this case, the amount of force that is required to be given to this object so that both the objects move with the same velocity. So it is like if you have a heavy stone and a very small stone, the amount of force that needs to be given on the stone so that both move with the same velocity. So how much force you have to apply? If the object is huge, you have to apply more force. That is very obvious, right? So in this case also, the force that is required to push this heavier mass is greater than the force that is required to move the smaller mass, right? So greater the mass, greater is the force required to make it to start its motion, right? So what is the conclusion? Greater force is required to set heavier bodies in motion. Fine? Okay. Now let us look at the dependency of force on change in velocity. So how does force changes with the changes in velocity? Here if you see, you have two cars of same mass, absolutely identical cars. Now in the first case, the vehicle comes with an extremely high speed. The velocity of the vehicle is higher here. So the amount of force that is needed to stop this vehicle is more. But in this case, since the vehicle was coming quite slowly, the amount of force that you need to stop the vehicle is lesser. You can try this example with a toy at your home. If you have a toy car at your home, just try to bring it very slowly. If the car is moving very slowly, you can stop it by applying a little force. But if it is coming very fast and if you apply little force, it will not stop, rather it will hurt you and it will move ahead, right? But if you apply a greater force in that case, even the fast moving car will also stop. So that means the conclusion is that greater force is required to stop bodies moving with higher velocities. So that means if the object has greater mass, greater force is required. If the object is moving with higher velocity, greater force is required, right? Okay. So from this, what would we conclude? So we can see that force changes as the mass changes. Force also changes as the velocity changes. So we can say that force will change as the momentum changes. So we can say that greater the change in momentum in a given time, greater is the force that needs to be applied. Right? So how can we say this? We saw that momentum is the product of mass and velocity, right? And what did we saw in the previous two slides? Greater mass, greater force is required. Again, greater velocity, greater force is required, right? This is what we saw. So now let us suppose that you have some object. So now let us suppose that we have some object. There is some object which has mass m and velocity v. So what is the momentum of that object? It is mv. Now let us suppose that the same object, after some time, its mass increases to m dash and the velocity increases to v dash. So what will be the momentum after some time? It will be m dash v dash, right? So what is the change in momentum? Change in momentum is nothing but p dash minus p, right? So that is equal to m dash v dash minus mv. Fine. So now we saw that as mass increases, force increases, as velocity increases, force again increases. So force is directly proportional to mass, force is directly proportional to the change in velocity. So from this we can say that force is directly proportional. Since force is directly proportional to mass, force is directly proportional to the change in velocity. So force should be directly proportional to the change in momentum. So that means greater the change in momentum, greater is the force that needs to be applied. So that is why this statement has been given, that greater the change in momentum in a given time, greater is the force that needs to be applied. Right? Okay. So now let us look at a practical example of this change in momentum. Have you ever observed, while seeing a cricket match, have you ever observed the way a player catches a ball? Now, the ball has been thrown, when the batsman bat it or when somebody throws a ball, the ball is moving with a very high speed, right? Now, what happens? There are two scenarios. In the first case, so I have named it as Dhoni versus Ronie catching a ball. So Dhoni is somebody who is experienced, who is a good player. And Ronie is somebody who doesn't know how to play well and he is a newcomer, right? So what happens? In the first case, if it is Ronie, that means if it is a newcomer. So this is Ronie and this is Dhoni, right? So when it is Ronie, how will he catch the ball? The ball is coming with high speed and he is just keeping his arms like this stationary. So the ball which is coming with a very high speed falls on his hand and his hands get hurt because the ball is coming with high velocity. You can just try it on your own if you want to hurt yourself and also want to verify this. You keep your hands stationary, you do not move your hand, let a ball which is coming at a very high speed to fall on your hand. What will happen? That ball coming with a high velocity will hurt your hand. But in the second case, when Dhoni catches a ball, what does he do? When the ball comes, you would have observed, please observe this very carefully when you watch a cricket match. The player always will make their hands also move along with the ball. With that, what will happen? They are actually making their hands also move, and as a result, the force which is required to change the momentum vector is given by hand. Right? So when your hand also moves, you are actually not hurting yourself, right? Because in the first case, what is happening? The change in momentum is more. So the amount of force that is being exerted on your hand is also more. But in this case, since you are also moving your hand, the change in momentum, because the hand is also moving with some velocity, ball is also moving with some velocity, right? So the change in momentum in this case is lesser. As a result, the force which is required in this case is also lesser. As a result, the player is not hurt. Do you understood? So in this case, the change in momentum is more because the ball is moving with some velocity v and the hand is stationary, that is velocity is 0. But in this case, ball is moving with some velocity v, the hand is also moving with some velocity v dash. Therefore, the change in momentum here is less. As a result, lesser force is required to stop the ball and therefore the hand is not hurt or the player is not hurt. Right? So, see, these are some of the things which happens in our day-to-day life. Even a cricketer who does this technique to catch a ball, I'm not sure if he knows the funda of momentum or not. So, there are so many things which keep happening around us in our day-to-day life, but we are not aware of the concept behind that. Right? For example, just now, before some time, I talked about the inertia example, right? The jerks which we feel when we are in a car and brakes are applied suddenly. So these are some things which we keep experiencing, but we do not know the concept, but we do not know the reason behind that, right? Okay, so with this, I think you got fair idea about momentum. What is momentum? It is product of mass and velocity. Force and momentum are very closely related. As the change in momentum increases, force also increases. Right? So with the help of this, Newton gave his second law. So Newton's second law stated that the rate of change of momentum of a body is directly proportional to the applied force and takes place in the direction in which the force acts. Okay, so according to Newton's second law, so that means this force is directly proportional the rate of change of momentum. So rate of change of momentum can be written as dp by dt. Now again, you must not be aware of the rate of change of anything. In the previous chapter I was mentioning this, right? Rate of change of momentum, what does that mean? That means the change of momentum per unit time. So that can be also written as the change in momentum with time, right? So force is directly proportional to the rate of change of momentum, right? And it also says that the rate of change of momentum takes place in the direction in which the force acts. In the previous example, the player catching the ball, you saw the same thing. The change in momentum and the force, they both act along the same direction, right? Now, since force is directly proportional to the rate of change of momentum, we can convert this proportionality into an equality sign, but for that we will have to put here a constant. So we have taken that constant as k. Now the value of this k is taken as 1, and therefore force becomes equal to dp by dt. Right? Now this dp by dt can also be written as, alternatively, the second law is also stated as the relationship between an object's mass and its acceleration and the applied force is given by force is equal to mass into acceleration. The direction of the force vector is the same as the direction of the acceleration vector. So here force is a vector quantity, acceleration is also a vector quantity. So it says that if there is an object with mass m which moves with an acceleration a, then the force acting on that body is given by mass into acceleration. So here force and acceleration, they both act along the same direction. So these both statements, that is force is rate of change of momentum and force is equal to mass and acceleration, they both are actually the same. They both are synonymous, you can say that. So we will prove that in the next slide. We will try to derive force is equal to mass into acceleration. So from definition, we saw that force is nothing but rate of change of momentum, right? Now you keep d by dt aside. What is momentum? Momentum is mass into velocity, right? Now this becomes equal to mass into dv by dt. Now what is rate of change of velocity? In our previous chapter we spoke about that. Which is that quantity which talks about the rate of change of velocity? Right, it is acceleration. So this can be written as mass into acceleration. Therefore, we saw that force is equal to mass into acceleration is nothing but it is another form of writing force is equal to dp by dt. So from Newton's second law, we found that for any object on which an external force F is acting, that F is given by the product of mass of that object and the acceleration of that object. Right? So this was Newton's second law, and this law was very, very significant, and it since it became very general. Like the first law, it only talked about uniform motion. The second law gave a mathematical relationship for any kind of motion, for any kind of non-uniform motion, right? That it gave a relationship between force, mass and acceleration, right? Okay. Now, what is the unit of force? According to this, we can say that force can be written as kg meter per second square, because kg is the unit of mass and for acceleration it is meter per second square. But SI unit of force is Newton. Now, let us see how is the second law consistent with the first law. I mean, whether the first law and the second law consistent with each other. First law talked only about uniform motion, and second law is now talking about non-uniform motion. Now, is the second law applicable for uniform motion? Now, what does my second law say? My second law states that force is equal to mass into acceleration. This is what my second law states. Now, if force is equal to 0, if the external force acting on the system is equal to 0, then what will happen according to the second law? Then according to the second law, acceleration will also be equal to 0, right? Acceleration is equal to 0. What does that mean? Acceleration of a body is 0. That can mean two things, right? Body is at rest or body is in uniform motion, because when the body is moving with uniform velocity, your acceleration is 0. We have talked about this in our previous lesson, right? So from second law, we saw that in the second law itself, if the external force is 0, then the body is either at rest or it is in uniform motion. And what does our first law say? First law says that if the body is at rest or if the body is in uniform motion, that means if the acceleration is equal to 0, then the net force acting on the body should be equal to 0. So both of them are telling the same thing, right? So my second law is consistent with the first law. So we can say that the second law is true not only for non-uniform motion, but it holds true for uniform motion as well, right? So the first law and the second law are consistent with each other. We will now talk about another quantity known as impulse. So what is impulse? So why am I talking about impulse? Since we talked about momentum, it is good to know what impulse is. So impulse is another quantity which is defined as force multiplied by time it takes over. That means when force is acting on a body, for how much time the force actually acts on that body, that is known as impulse. So the product of force and time it acts over, the time duration for which the force actually acts on the body. So that time multiplied by force gives us impulse. So let us look at the example of the tennis racket striking the ball. So when you strike the ball with the racket, for some period of time, the force actually acts on the ball, right? So that time multiplied by the force gives you the impulse, right? So impulse is also written as the change in momentum. Why do we write that? Because as per definition of impulse, what is it? It is force multiplied by the time for it acts over, right? Now what is force? By definition, from Newton's second law, we saw that force is nothing but change in momentum per unit time, right? So this time and this time will get cancelled. Therefore, we can say that impulse is equal to change in momentum, right? Okay. With this, we ended our second law of motion as well. So now it's time to start with Newton's third law of motion. So let us quickly see what does the third law of motion state. The third law of motion states that to every action there is always an equal and opposite reaction. This is the most popular law of motion. Most of the times you will see people will say every action has equal and opposite reaction. That means for every force which is acting on an object, there is an equal and opposite force which is being exerted on that object, right? So this law is a very interesting one. Let us suppose this boy Ronie is holding a ball. So while holding the ball, he is exerting some force on the ball. The ball will also exert an equal and opposite force on Ronie's hand. So that is what Newton's third law stated. Now the force which is being applied by this boy on the ball, that is known as action. And the force which is being exerted by the ball in return, that is called reaction, right? So let us suppose if you have this object O, you apply an external force F on it. So this external force F is your action. Now when you apply this force F on it, this object will exert an equal and opposite force on your hand, and this force is known as reaction. This is called reaction because it is reply of action. When you give some force is exerted on you. So reaction is the reply of action, right? Similarly, this when I talk of this Newton's third law of motion, You must think of this example of the apple falling down the tree. This is the most famous experiment, not experiment, this is the most famous story related to Sir Isaac Newton. Once so happened that Newton was sitting under a tree and an apple fell on his head. This made him think that what attracted the apple, I mean, as soon as the apple was detached from the tree, why did it fall on the ground? Because it was attracted by the earth. So now the question which arose in his mind was that, now if the apple is being attracted by the earth, is not the earth attracted by the apple? So with this small observation, he started digging into force and motion, and he came up with these three famous laws of motion, which governed the entire classical mechanics. Right? So even in this case also, yes, a force is being exerted by the apple as well. But the difference is that since the mass of the earth is very large, therefore the force experienced by the apple is large, whereas the force experienced by the earth is very less, because the mass of the apple is very small as compared to the mass of the earth. That's what I told, right? If the mass is higher, the force needed to move that object is also more. So mass of the earth is so huge, so you need a lot of force to make it move. Will that small apple be able to exert that much force? No. Right? So that is why the apple moves, because the force experienced by apple is by the earth. So the earth can exert a large force on that small apple, and the apple can move. But that small apple cannot exert that much of force that can move the earth. Right? Okay. So as I mentioned before also, we will talk about the action and reaction forces. Action and reaction forces always act on different bodies. It is a very interesting thing to remember. Action, let us, as I mentioned before also, if this is your object O, action will act on object O, reaction will act on your hand. So if this is your hand, so action will act on the object, reaction will act on your hand. So action and reaction forces always act on different bodies. Action and reaction forces occur at the same instant. I mean, there is no time lag between action and reaction. As soon as some force is applied on an object, immediately a reaction will be applied in the opposite direction. So action and reaction forces occur almost at the same instant. Now, many people think that the relationship between action and reaction is same as a cause-effect relation. That means first action occurs and only after that reaction occurs. But it is not like that. Action and reaction occurs at the same instant. So an important thing to remember is there is no cause-effect relation between action and reaction. Cause-effect relation means, as I said, many people have this misunderstanding that action is the cause which gives rise to reaction. So reaction is the effect. But it is not like that. As soon as there is an action, there is a reaction at the same instant. So action and reaction occurs at the same instant. Right? And also, as I mentioned, they act on different bodies. For example, if action is force exerted by A on B, then reaction would be force exerted on B by A, and they are in opposite direction. So this is the force exerted on A, and this is the force exerted on B, as I gave this example of the object and the hand. Let us now talk about conservation of momentum. Now that we have already spoken about all the three laws of motion, it is time we can talk about conservation of momentum, because we have already spoken about momentum. So learning Newton's second law without having a good knowledge of momentum is incomplete. So that is why I introduced momentum before stating Newton's second law. Now that you are aware of the laws of motion, let us quickly look at the conservation of momentum. In an isolated system, the total momentum is conserved. That means the total momentum of the system will also remain the same. It can neither be created nor destroyed. So if any event takes place, before the event, the total momentum will remain the same as the total momentum after the event. So let us take an example for this conservation of momentum. Let us take the example of a spinning top. You would have seen this top which spins. Once you rotate it, it keeps spinning, right? So in this spinning top, if you notice, at every point, let us suppose if I consider this point. So for this point, maybe its momentum would be mass of the top multiplied by the velocity. If the momentum in this case is along this direction, there is some point on the opposite side where the momentum will be same in magnitude but in opposite direction. So similarly, for every point of the spinning top, at every point the momentum will get cancelled by another such point on the other side. So as a result, the net momentum would be equal to 0. So the total momentum will remain conserved. If total momentum remains conserved doesn't mean that the total momentum would be 0. The total momentum will remain conserved means that even though the top is spinning from one position to another position, but for the entire system, the total momentum will always remain the same. Somewhere the momentum will be less, somewhere the momentum will be more. But overall, the total momentum will remain conserved. So let us look at another example. When a bullet is fired from a rifle, so what happens in that case? How does the momentum remain conserved? So now let us consider the initial scenario. So let us suppose this is my initial scenario where the bullet is not yet fired. Right, so in this case, in the initial case, my momentum is equal to 0 initially. Right, now when the trigger is pulled, when you pull this trigger, what happens? The bullet gains momentum. When you pull the trigger, the bullet gains momentum and it starts moving with some velocity v. Right? Now the bullet is now moving with some velocity v in this direction, but at the same time the trigger is being moved along this direction. That is the rifle. This rifle as a whole is moving along this direction. So these two again gets cancelled in this case. Therefore the total momentum in this case is also equal to 0. Because here there will be some momentum because the bullet will have some velocity v. But there will be some movement of the rifle in the opposite direction. Right? So the initial kinetic energy was equal to 0. When the trigger is pulled, kinetic energy of both the gun and the bullet are positive scalars. Hence, don't cancel. Therefore, the total kinetic energy increase. Right? Now, when I am talking about momentum, see, initially momentum was also 0. Kinetic energy was also equal to 0 because in this case the gun is at rest, the bullet is at rest, everybody is at rest. For the entire system, momentum is 0, kinetic energy is 0. Now when you pull the trigger, what happens? Let us see once again. When you pull the trigger, you saw that the gun moved in this direction, right? So there with some velocity v dash. The bullet moved along this direction with some velocity v. Now let us suppose the bullet has some mass m, this gun has some mass m dash, right? Now in this case again, this total momentum of the bullet, that is mv, and the total momentum of the gun, that is m dash v dash, we are in opposite direction and then they will cancel out each other. Because see, v dash is very small when compared to v because velocity of the bullet is very high, but at the same time mass of the bullet is very small and mass of the gun is very high. So overall this m dash v dash will cancel out mv and therefore the total momentum in this case will also be equal to 0. But what happens to the kinetic energy here? The kinetic energy increases. So the kinetic energy in this case is not conserved, but the momentum is conserved. So you understood how the momentum is conserved. So initially also the total momentum was 0. Later also the total momentum was 0. Let us take another example of rocket propulsion. So in case of rockets also, we see that momentum is conserved. How? Let us see that. Now let us suppose that initially this is my rocket and the rocket has a mass. So mass of the rocket is capital M. Now let us suppose that the rocket just started moving. So just starts moving. So initially the rocket was at rest. Now the rocket just starts moving with some velocity v. Right? Now immediately as the rocket just started moving, after some time what will happen? Gases will get ejected continuously in the opposite direction. So now the rocket is moving along this direction, the gases are ejected along this direction. Correct? So now giving a forward push to the rocket. Now the gases which are getting emitted along this direction, these gases only give a forward push to the rocket, and that is how the rocket keeps on moving forward, right? So what keeps on happening, since the gases are getting ejected from the rocket, so mass of the rocket is decreasing now. So this was my initial scenario. Now let us look at the final scenario. In the final scenario, what would be the mass if the mass of the gases that is ejected is small m? Because of the gases ejected, let us suppose this much of mass of the rocket fuel has reduced. So now the mass of the rocket would be m minus m. And what would be the velocity of the rocket? Velocity would be v plus, let us suppose the velocity with which the rocket was moving was v, and the velocity with which the gases were ejected was v dash. So now the net velocity of the rocket would be v plus v dash, because this v dash is actually giving a forward push to the rocket. This v dash is also pushing the rocket forward. So the net velocity of the rocket becomes v plus v dash, right? So what do we see? We see that as the mass is decreasing, mass of the rocket is decreasing, the velocity is increasing, such that mass into velocity remains constant. So initially, what was the momentum of the rocket? It was mass into velocity. Later, when the gases got ejected, mass kept decreasing, but at the same time velocity kept increasing, so that the product mass into velocity can still remain constant. So in this case, you can see that the total momentum is not zero, but the total momentum is conserved. Initially also it was mv, later also it was mv. Even though changes took place, even though mass kept decreasing, but to keep that mass into velocity constant, v kept increasing, right? Because if in a product of two quantities, if one quantity increases, if you decrease the other quantity, then the product will again remain the constant, right? So this is the concept of conservation of momentum. That means processes take place, changes keep taking place, but still the momentum of the system remains constant. Now let us talk about collision of two bodies. This is a very important example of conservation of momentum. I mean, discussing conservation of momentum without collision is like absolutely incomplete, right? So now let us talk about collision. What is collision? The word collision means striking of two objects. When two objects collide, we say that a collision took place. But anyways, the literal meaning of the word collision is also, it means striking of two objects. So now let us suppose we have two objects, 1 and 2. Now let us suppose this object 1 has mass m1 and it is moving with velocity v1. Let us suppose this object 2 has mass m2, it is moving with some velocity v2. Now this 1 keeps moving along this direction, 2 keeps moving along this direction, and then what happens? They collide. So 1 and 2, they collide. And what happens on collision? After collision, there are different possibilities which can take place. Maybe 1 and 2 will get merged together. Maybe after collision, 1 kept moving along this direction, 2 kept moving along this direction, or maybe after collision, 1 went back, 2 also went back. Maybe they collided and they bounced back, right? 1 and 2 came from two directions, collided, bounced back. One possibility is they came together and then they stuck together. They became one. And then again they started moving together. Another possibility is they came, they collided with each other and then they crossed each other. That means 1 came like this, 2 came like this, they collided, 1 kept moving like this, 2 kept moving like this. So there are different scenarios, there are different things that can happen after collision, right? So this conservation of momentum says that the total momentum before collision is equal to the total momentum of the system after collision. That means whatever possibility happens. So this actually represents collision. So it says that the total momentum before collision will be equal to the total momentum after collision. Now let us consider case 1. In the first case. Now let us see what is the total momentum before collision. Let me denote that as P1, and P1 is equal to total momentum before collision. That will be momentum of 1 plus momentum of 2. Momentum of 1 is m1 v1 and momentum of 2 would be m2 v2, right? So m1 v1 plus m2 v2, but v2 is in the opposite direction, so you have to incorporate a negative sign here. Right, so this is the total momentum before collision. And what is the total momentum after collision for case 1? What is the total momentum? P2. That will be mass into velocity. So what is the mass here? Mass will be m1 plus m2 because both have merged together, m1 plus m2, and this is moving with some velocity, let us say v. Now what would be the total momentum in case 2? That means if 2 keeps moving in this direction, 1 keeps moving in this direction. So in this case, it will be m1 maybe with some velocity. Now the velocity will change after collision. So let us suppose 1 is moving with v1 dash, 2 is moving with v2 dash. So this will be m1 v1 dash plus m2 v2 dash. Similarly, in case 3, what would be the total momentum after collision? In this case also it will be m1 v1 dash plus m2 v2 dash. Please remember to put signs for velocity. For example, here both are in opposite direction, so this should have a negative sign. Similarly, in this case also this is in opposite direction, so this should have a negative sign, right? So now as per conservation of momentum, P1 should be equal to P2. That means this initial momentum should be equal to the final momentum. So this concept will become clearer to you when we solve problems. We are going to solve a lot of problems on conservation of momentum. The concept is that the initial momentum of a system will always be equal to the final momentum of the system. Right? Now, whatever process might take place in between. For example, here collision took place. In case of rocket propulsion, so many things happened. The gases started getting exhausted, the velocity kept increasing. So those were the changes. So even the changes take place, your momentum will remain conserved. The total momentum of the system will remain conserved. So with this, I will end this lesson on force and laws of motion. So I hope that I have been able to explain you what is the cause of motion, what causes motion. It is force. So when we talk of force, we should know balanced and unbalanced forces, because balanced forces are the one which do not cause any change in motion, and unbalanced forces are the one which cause a change in motion. So then we talked about the 3 laws of motion which were given by Sir Isaac Newton. So I hope I could explain you the first law, which stated that a body at rest will remain at rest and a body in uniform motion will remain in uniform motion until and unless you apply some external force on it. Then we talked about the second law, which told that force acting on a body is always equal to the product of mass of the body and the acceleration of the body. It also told that force is nothing but rate of change of momentum. So the second law was a more generalized law which talked about bodies in uniform motion as well as non-uniform motion. Then came the third law, which said that for every action there is an equal and opposite reaction. So these were the 3 laws of Newton. After that, we also talked about momentum. What is momentum? What is a change in momentum? What is conservation of momentum? And conservation of momentum is something which holds true in most of the scenarios taking place around us. Now, on the basis of whatever we studied in this lesson, we are going to solve a number of problems so that the concepts which you learned theoretically, because so far I was concentrating more on the theoretical concepts. I was telling you stories, what Aristotle told, what Galileo told, what Newton told, things like that. Now we will try to solve problems and we will see how the theoretical concepts will actually apply to the problems. Right? Okay.
I hope you enjoyed this video and you also got a very good understanding of the laws of motion and conservation of angular momentum. In the next video, we are going to solve numericals, because numericals scare a lot of children. They feel that they understood the theory but not really sure of how to solve a question. So the next video is dedicated for all of you, so be with us.